Hello, everyone. Today, I am excited to introduce our research on why SDF reconstruction benefits from heat diffusion. In this talk, I will walk you through some overlooked pitfalls in existing methods and share a surprisingly simple solution that addresses them effectively. This work was published at CVPR this year, and we are honored that it was recognized as a highlight. Let's begin with the background. As we know, implicit functions can represent surfaces in a smooth and continuous manner, where the surface is defined as the zero-level set of the function. There are various ways to define an implicit function. We can use analytical expressions or discrete representations, such as voxels or grids. In our work, we choose to use neural networks to represent the implicit function. Neural networks offer strong expressive power and make it straightforward to compute gradients. Compared to voxel or grid-based methods, neural representations do not require interpolation, which leads to cleaner and a more compact surface modeling. However, implicit representations can store much more information than just the zero-level set. Instead of focusing only on the surface itself, we can encode meaningful values throughout the entire space. One common example is the occupancy field, where the output indicates whether a point is inside or outside. If a point is definitely inside, the output is close to -1. If it's confidently outside, the output is close to +1. Another powerful representation is the signed distance function, which encodes the shortest distance to the surface, with the sign indicating whether the point is inside or outside. Now, let me show you why it is important to store accurate distance values to the surface. There is a key application of the signed distance function called sphere tracing. In this method, we use the distance function to estimate where a ray intersects with a surface and then render the surface. Here is how it works. At each step along the ray, we use the current distance value to safely jump forward. However, if the predicted distance is inaccurate, the algorithm becomes inefficient. For example, if the ground truth distance to the surface is 5, but your prediction is 6, the ray will overshoot the surface. Then, the algorithm needs to take one step back and try again. It requires repeatedly testing smaller and smaller steps until the result is below a certain threshold. This leads to many redundant queries. On the other hand, if you have an accurate distance function, the ray can converge to the surface with just 2 distance queries. It could improve both speed and accuracy. So, having a high-quality signed distance function is crucial for applications like this. Let's now go to our task. In this work, we define the problem as follows. Given an input point cloud, our goal is to get a signed distance function that represents the distance to the reconstructed surface. The output is positive when the point is outside and negative when the point is inside. In this figure, you can see an example of a poor reconstruction. The zero-level set is okay, but the surrounding level sets are unreliable. A good SDF, however, should not only recover an accurate zero-level set, but also produce meaningful and consistent values across other level sets as well. Since we are using neural networks to represent the signed distance function, we denote it as U theta, where theta represents the network parameters. To reconstruct an accurate SDF, we need to train the neural network using an appropriate loss function, or more often, a combination of losses. So the question is, how do we design this loss? Let's first take a look at an ideal signed distance function. Given the input point cloud on the right, we can visualize its corresponding ideal SDF on the left. In this case, it looks like a retcon. We can also visualize the gradient of this field. One obvious piece of information we can use is that for all points on the surface, the output of the SDF should be almost 0. In practice, this leads to a simple constraint. We can minimize the absolute value or the squared value of the network output at these surface points. This is commonly called as the boundary loss. However, this loss alone is not sufficient. If we only optimize for 0 values on the surface points, the network just provides 0 everywhere, a solution that completely fails to reconstruct the distance field. What do we need? Let me show you the first group of candidates. These methods are based on some properties that a perfect SDF should be. For example, the norm of gradients should be 1 almost everywhere. This is known as the eikonal equation, and it was first introduced for SDF optimization in 2020. If we assume the surface is made of polylines, we can also observe that the SDF should be almost flat in most areas. This gives us another condition that can be used as a loss. A more complex property is that the determinant of the Hessian should be 0 almost everywhere. Why? Because at each point, you can always find a direction with no curvature. In the Hessian matrix, this means there is an eigenvector with eigenvalue 0, so the determinant becomes 0. However, all of this only work as necessary conditions. They are not sufficient. You can always find another function that satisfies all of them almost everywhere, but still is not a valid SDF. Let me show you an example. If you start from a bad initialization or introduce a small disturbance during optimization, the result can go wrong. In this 1D case, the 2 red points are boundary points. Even with the eikonal loss, the optimization result, shown as the red line, is far from the ground truth, shown as the gray dashed line. The second image shows the divergence constraint, which assumes the level set should be flat everywhere. So the loss can be minimized, but the result is still not close to the ground truth. It still fails to converge to the correct SDF. In short, since these are only necessary conditions, they cannot guarantee convergence and do not rule out invalid solutions. Now let's check the second group of candidates. Some other researchers believe that the network should directly reproduce the distance to the point cloud. However, if you check our definition from the previous slides, you will see that this idea is unreliable. For faraway points, this approximation works well, so people use either the original distance value or its direction to train the neural network. One thing I want to point out is that the computational cost of this method is high, because for each query point, you need to visit the input point cloud, and you need to find the closest one and compute the distance to use as a reference for training. Even with some tricks like BVH, it's still a cost. However, for points close to the surface, this candidate fails, because it only learns the distance to the point cloud, while our task is to reconstruct the distance to the surface. Another sad fact is that in the sphere tracing algorithm, most queries happen near the surface. As a result, the predictions in these regions can be quite inaccurate and chaotic. The good part for this is that for points far away for the surface, the level sets look fine. However, for surface reconstruction and distance queries near the surface, the outcome is very poor using the first condition here, that it just constrains the F with the distance to the boundary points. And this method is called SAL. This time, we design one loss to solve all of these problems. You can observe this 1D case again. We compare our method with the eikonal loss. If you only use the eikonal loss, you cannot converge to the real distance function. However, with our method, you can easily converge to the correct distance function. We also test on some complex topologies with a lot of hosts. This is a high genus dataset created by Ishit Mehta. Our method is the only one that can accurately reconstruct the surface and provide accurate level set reconstruction. This slide also shows more problems with previous methods. For example, they are not very stable. During training, the result may flash once and then get stuck in a local optima. Another issue is that they need to introduce an area loss to remove extra boundaries. However, with our method, you do not need any extra area loss, and you can easily remove all the extra boundaries. How did we do that? We found a very interesting connection between heat simulation and distance reconstruction. If you simulate heat and reach thermal equilibrium, you will notice that the temperature decreases monotonically with respect to the distance. To reconstruct a good distance from heat, you just take a log transformation, and vice versa. If you want to get a good heat simulation, you can take the exponential of the ground truth distance. So there seems to be an interesting connection here. In this slide, I will show you that what equation controls the heat diffusion. This is called the screened Poisson equation. It describes thermal equilibrium with a spatial absorption term. This equation can also describe many physical phenomena, like plasma. In this figure, you can see a large positive charge can activate many negative charges around it to screen the electric field. This is also modeled by the same equation. But for easier understanding, we choose to explain it using the thermal background. You can see the figures here with different lambda values. This lambda controls how strongly the space absorbs heat. We want the temperature to show an exponential decay, so we let the heat diffuse from the boundary. If lambda is too small, the inside region won't show a clear decay, but when lambda is larger, the exponential decay becomes very clear. This connection is not just our intuition. Back in the 1990s, Vargham proved that when lambda goes to infinity, the temperature will exactly converge to an exponential decay with respect to the distance from the heat source. We went one step further. We proved that the convergence speed is linear with respect to 1 over lambda. Here we also show that how could we transform heat to the distance, and this reconstructed distance will be very close when lambda is very large. Like many other methods, we need to use a boundary loss. The second loss is to enforce the screened Poisson equation here. A very basic approach is to minimize the difference between the two terms, hoping them become as close as possible. However, we choose the energy method. We know that minimizing the falling energy leads to a minimizer that solves this equation. The first way is unstable, while our method is fast, stable, and robust. Let's do some quick math to verify why the minimizer solves this equation. The connection between them is given by the Euler-Lagrange equation. By applying this equation and computing the symbolic derivative to the h and the gradient of h, you will find that these two terms are easy to get. One important point is that the divergence operator here means the full divergence, not just a symbolic term with regard to the gradient of f. By this verification, we know that minimizing this energy indeed gives the solution to the heat equation. However, our neural network only outputs the distance. So how can we use this energy to improve the distance? It's actually simple. We don't need to simulate heat explicitly. Because we know the log and exponential transformations, we can just apply these transformations and hope that after this, the exponential term minimizing the energy. That is, we simply do a variable replacement. As a result, there's no need to explicitly optimize h. After this transformation, we get a new version of the energy, now written in terms of U. And this is the heat loss that we are using to optimize the SDF. Since our method guarantees convergence to the true distance function, we can beat the first candidate. But the next question is, how do we beat the point cloud distance-based optimization? The reconstructed distance should reflect the distance to the heat sources, not just the original point cloud. This is a key detail that many previous methods overlook. In our simulation, we model the distance to the heat sources only. So why are there more heat sources than just the point cloud? Let's go back to the equation. It says that wherever h is equal to 1, it becomes a heat source. The final temperature is only determined by how far the closest heat source is. Even though we apply the boundary laws only on the point cloud, the neural network is smooth and continuous. It can connect the points and merge them into a whole surface, where u is equal to 0 and h is equal to 1. Let's just use this figure to explain. Because u flips sign inside and outside, so on the boundaries, u is equal to 0 and h is equal to 1. Then the entire surface acts as a heat source. As a result, the final temperature is determined by the distance to the surface. Any query point will be influenced by the whole surface, not just the sparse points. That's why our method gives accurate distance reconstruction near the surface. The next question is, how does our method minimize the surface area? At first glance, it seems like adding more heat sources into the boundary set might create extra surfaces. However, we proved that minimizing heat loss actually minimizes an upper bound of a surface area estimator, which is given by Pomarola. This also makes sense from a physical perspective. The boundary loss anchors the surface by enforcing h is equal to 1 continuously along the boundary, and it also maintains a stable heat flow during optimization. But for fixed surfaces without any true boundary points, the heat flow cannot be sustained. So, these surfaces gradually get absorbed, smoothed out, and eventually disappear. Their method needs an explicit area loss to remove extra surfaces. Ours doesn't. No need for any unnatural or handcrafted terms. And one more important point is that we also proved that using area loss distorts the level sets and leads to inaccurate distance queries. Then I will just do a very quick check for the stability analysis. For the temporal part, the function will be updated a little bit after every iteration. In frequency space, partial differential equations can be treated as ordinary differential equations. Our gradient flow will always converge. However, if you are only using the eikonal loss, the gradient flow may diverge in frequency space where the kappa E is smaller than 0. This is a visualization for the stability of the spatial part. You have some disturbance near the boundaries. Our loss could localize the small distance disturbance to a small region. With the eikonal loss, it may spread the small disturbance to infinitely far away. That's why we can be fast, stable, and robust. Let's show some results here. In the first row, for the point cloud distance-based optimization, you can see that level set reconstruction is acceptable in far regions. However, when getting closer to the surface, the results become terrible. In the second and third rows, these methods cannot effectively remove extra boundaries, nor provide accurate level sets for distance queries. In contrast, our method without any area loss effectively removes all extra boundaries and delivers a smooth, neat level set almost everywhere in the space. Another interesting thing is that if you zoom in, we are also the only one that provides accurate distance queries near the surface. This time, we present a harder challenge for all methods, a Voronoi sphere with many holes. We also created double layer and triple layer versions. Although it has 3 layers, our method can effectively reconstruct the SDF within 10,000 iterations. In contrast, their method requires 10 times more iterations and still fail to produce acceptable results. Their level sets are chaotic, surface reconstruction is terrible, and they cannot remove extra boundaries. We also tested our method on a larger dataset called ShapeNet. Our method provides accurate distance queries almost everywhere in the space. In the first 3 columns, you can see that overall, our method performs nearly the best, only slightly worse than the SAL method in RMSE and MAE. Because, as I mentioned, SAL is a point cloud distance-based optimization with acceptable approximation for far regions. However, within a closed region, we arbitrarily choose within 0.1 distance to the surface. Our method outperforms all others by a large margin, showing much better accuracy near the surface. On this slide, we show that our method uses fewer loss terms and much fewer training iterations, and we do not need to visit the point cloud to find the closest points, and we also don't require second-order derivatives. That's how we can be much faster than other methods. Finally, let's go back to the sphere chasing algorithm. Thanks to our accurate distance queries, we achieve faster rendering performance with lower computational costs. The visualization here illustrates the number of distance queries required per pixel. Brighter regions indicate higher computational cost. On average, our method outperforms all previous approaches. Finally, let me summarize our contributions. First, our method outperforms optimization approaches based on insufficient conditions. These methods cannot rule out non-SDF solutions and lack convergence guarantees, while ours is a sufficient condition. Second, we improve over point cloud distance-based optimization. Those methods struggle to accurately reflect distance to the reconstructed surface. Third, our method does not require an extra loss term to remove redundant surfaces. It mathematically bounds it and physically direct. Lastly, we made the whole optimization more stable. For more details, please check our paper. We are also very happy to answer any questions. Feel free to reach out to us. Thanks for your listening.